Good afternoon, class. I'm back again. We're going to try to maybe finish the compressed air slides here in this session. I have some other things that we may do for class on Thursday. I view this as the continuation of the lecture already posted on, I think yesterday for Tuesday, December 1st. So let's get moving into compressed air use here. This just shows a bunch of different pneumatic tools. Hopefully you can read it. You just see there's all kinds of stuff out there. Pneumatic tools are very, very handy. They're cost effective. They probably cost less than electrically motor driven because you don't have to buy the motor, you know. And you just hook a flexible pneumatic line into most of these, and you just clip it in, and the thing's ready to roll as long as you have a supply of compressed air at adequate pressure. So you can see, my gosh, we got paint sprayers, we got hydraulic lifts, we got air hoists, we've got car lifts, bus lifts, cut-off tools, grinders, garage door openers, I mean, all kinds of stuff. My goodness, I can't read them all. And you get some kind of an idea of the average free air consumption. So that would be of the rating of the compressor. So if we had our 100 horse compressor that was rated at 500 CFM output, you get an idea how many of these tools, like a jackhammer requires what, 135. So if you're going to power, 3 jackhammers, I guess you could do that with a 100 horse air compressor. They're going to be operating at the same time. And here's just a few more for good measure, in case we didn't have enough on the previous slide. Okay. We want to talk so these slides kind of concentrate on inappropriate uses for compressed air. Because those represent an opportunity to do something else, not use compressed air, which is so expensive. Maybe we can save some money and still accomplish the same task. So personnel cooling, you're not supposed to spray compressed air on yourself or expand it through an orifice and cool it down and then blow it on yourself. Parts ejection, that's considered inappropriate. A lot of people do it, but if you're stamping parts or somehow manufacturing parts and you have to get them out of a mold or something, it'd be good if you could find a way other than blowing compressed air. Idle equipment, it says use solenoid valves. The idea is there, if we have lines, sometimes you'll have maybe a big manufacturing line that's supplied by maybe a 2 or 1.5, 2, 2.5, 3-inch compressed air line. When that whole system goes down, it may have a general power switch, and you can put a solenoid valve that will shut off the air to that line because you're not manufacturing anything. And so any leaks that are down that past that solenoid valve will be de-energized, and so you won't leak any air. And I mean, it's good to detect and fix leaks, but we can never, on a big system, you're not going to get them all, and they continue to grow back. So this is a way, if these lines are down significant length of time, it's a way to avoid any leaked compressed air. Or you may have open blowers, that sort of thing, blowing applications down there, and that will de-energize those. So that's a good idea. If it depends on the length of time it's down and how much you think it could save versus what the valve would cost and the control of it. Open drains. We don't want to just crack drains open to drain condensate, anything from the system. We want to have use traps. And we also want to treat potentially that water if it's a lube injected compressor. A lot of times there's compressor lubricant in the moisture, and that needs to be removed before we try to put it down the sewer. Shaft bearing coolers, they make these, they call them air horns, and they you plug a compressed air line into it, and these things are portable on stands. And if you have a bearing, something that's running hot, you can just blow compressed air through this air horn and it'll cool them down. Pretty expensive cooling. So the idea would be, and if you need to do that, you do it for a very short period of time, and then you make a repair, replace the bearing, or figure out why it's running hot, and then get that fixed. Low pressure conveying and vacuum generation. We can generate, have a venturi, blow air through it, and then the connecting line on the side of it, that will cause a vacuum. So you can generate vacuums, not tremendously hard vacuums, but you can get pretty significant vacuum with a venturi type vacuum generator, but you're blowing compressed air all the time, which is expensive. You could probably do a vacuum pump and use a lot less electricity, even though the vacuum pump will probably cost you more. Low pressure conveying, sometimes we blow dilute phase systems or dense phase systems. We use air to blow materials from one place to the other. Leaks, talked about those. High delta P and components, consider low pressure drop disconnects. So what that means is sometimes we'll have, a nice big compressed air distribution line, and we'll come off of it with a 1/2 inch line or even less than that going to a use, and we have a huge pressure drop across that last little piece of line, which then causes us to jack up the compressor pressure. Whereas if we put in, instead of a 1/2 inch line, we put in a 1 inch line, which wouldn't cost very much in most cases, then we could lower the compressed air pressure, or certainly not raise it, and save a considerable amount of energy. Cabinet coolers, those are vortex devices. You expand it through an orifice and it gets cold. And so a lot of electrical cabinets will have cabinet coolers, and they actually do a couple things. If you blow the compressed air in there, you can again drop pressure, and it provides cooling, and it also pressurizes the electrical cabinet and prevents dust and other elements outside the cabinet from entering. If you're doing that to keep particulates and dust out, that may be hard to avoid. If you're doing it for cabinet cooling, you can find less energy intensive systems, or you can at least get a vortex cabinet cooler that has a thermostat on it so that it only blows compressed air in, say, in the summertime when the temperature's up and the cabinet really needs to be cool. Air motors, they're very convenient. People use them to stir paint in barrels, to pump slurries, all kinds of stuff. They're very portable. You can carry the thing up, set it down, put a couple concrete blocks on it to hold it down, hook up your lines to it and your compressed air, and bingo, you're pumping. So you don't have to pull electricity to it and conduit and all those sorts of expenses. But again, compressed air is expensive. Air hose blowing, just blowing material off the floor, etc. Air vibrators, maybe you have to vibrate a tank or something. Maybe it's paint, you want to vibrate it to keep it mixed. Again, they're motor driven units. It would use a lot less energy, but again, you have to do the wiring and all that. So that's a more permanent type installation. Sparging, blowing air out into a tank in order to mix it, works really well, but again, it's pretty expensive. Diaphragm pumps, that's another type of pump they used a lot to pump slurries, that sort of thing. And there's many, many others. So just a quick list. Here's a picture of sparging. So you see, what are these? These look like at least 1/2 inch compressed air lines down in this tub or this barrel. And man, if we put 100-pound air through this thing, this doggone thing's going to churn like crazy. So you would get unbelievable mixing, but you're paying a lot of money for it. And this just shows a cross-sectional area, what that might be all about. Low pressure applications often can be accomplished with fans or blowers. I think I think I may have mentioned this in class, I can't remember, but Fleet Guard here in town, they make filters for, I guess, oil filters and air filters, and they make their filter media. They have a process and they use compressed air and they mix up this slurry of kind of pulp, and I don't know, it's a secret recipe, but they can spray this stuff out on a mold, and when it dries into filter paper. So they spray them on the molds, and then once they dry it off, and then you got a filter. Well, they use compressed air to spray with, and I was out there. This was a number of years ago, and they had 400 horsepower rotary screw air compressors, to a lot of which went to the filter media area. They generated air at 100 pounds of pressure, and then they proceeded to drop it to 10 to 12 pounds in order to spray in the media center. What a waste. Pump it to 100, drop it to 10 or 12. You can get a blower that would easily go up to 10, 15, 20 horsepower. I mean pounds per square inch, and use probably 20 to 30% of the horsepower, save a bunch of energy. And Fleet Guard did have other plants around that used blowers. This plant in Cookeville was older, and it got designed around compressed air. I don't know if that's ever been changed. I haven't been out there in a number of years, but there was a recommendation made to change it, and they knew it was a big waste. Okay, so two-stage blower can get you kind of the top end is probably pushing 30 psi. Anything that and anything above is really termed a compressor instead of a blower. The work of inefficient air motors can usually be done more efficiently with an electric motor. And the big caveat there is if we have a hazardous or explosive environment, those electric motors, produce sparks down inside the windings and all that stuff. And sometimes that's not acceptable. And so that is one reason that pneumatic motors may be used. We can determine when vacuum requirements often can be served more efficiently with a vacuum pump rather than by compressed air operated with a Venturi nozzle. So vacuum generation, those are three big ones. That's just a picture of some blowers. There are different configurations of them on the market, but easily can produce 20 and up to 30 PSIG. And so here it states that we can do that and use maybe only 20% of the energy of compressed air, taking it up to 100 and dropping it back. And a picture of a little pneumatic motor. Here's a slide on the vacuum generation. So we supply compressed air to the end of this and blow it through this. It's kind of like a Venturi effect. It goes through the small opening and opens up, and then it pulls that action across this open pipe. So it kind of sucks air or whatever gas is down here, probably air, out of this. And so then we get a vacuum generated in the pipe that connects right here. And then all of this just blows to an exhaust. So we just sit there and blow compressed air all day. Works real well. Not much in the way of moving parts, but it's pretty expensive. Compressed air used to blow off debris. We have various, implements, wands, and that sort of thing. Some of them that shows the curly cord that hooks into the compressed air supply. And you just, push the handle and you blow compressed air like crazy to move stuff around. There's a diaphragm pump. So you supply compressed air to these things, and it kind of pushes the diaphragm back and forth, which then pumps material through this. And like I said, a lot of times fluids that have a lot of particulates in there, they particularly like to use these diaphragm air pumps. Filter cleaning with compressed air, a bag house. that has filters in them called bags, often cleaned with compressed air pulses. And so what happens is maybe you have dust being generated in a process, and so you have a fan that is outside blowing or sucking this dust laden or dirt laden air through this bag house, and the bag house is full of these bags, and the fan moves the air through, and the air and the particulates hit the outside of the bag. The air goes through the bag and comes out, and then is just blown on through the fan, and usually there's a stack that blows it up, maybe 25, 30 feet in the air, but it's been cleaned out. So environmentally, it's okay. It could be pulling air conditioning or heat out with it, but if you have a process generating a lot of dust, you have to control the dust. And then, so the dust accumulates on the outside of the bags. And so ever so often, there's a compressed air line, and it'll have a little solenoid valve, and it'll open and blow a burst of compressed air down on the inside of the bag, which then goes in the opposite direction through the bag and knocks that dust cake off, and there'll be a hopper or something down there to collect it. So we can save money sometimes on these things if we only pulse when we measure a certain differential pressure across the bag, indicating that it's dirty and needs to be pulsed, because the dust loading may change from one shift to the next, 1 hour to the next during the day. And the cheapest control is to pulse on time. But if you have a bag that's not dirty, you don't really need to pulse it. And pulsing it does damage to the bags. They only can withstand a certain number of pulses. So by pulsing on differential pressure, you reduce the number of pulses, which extends bag life, and it actually cleans better. The bags clean more efficiently when they have the dust cake on them, because the dust cake is additional media that the particulates have to go through. So that's a good option. And in some of the energy studies, we sometimes recommend that a plant change the controls on their bag house compressed air pulsing equipment to pulse on differential pressure instead of time. It's a good idea to clean rows apart from each other in a sequence. So, because if you do them right side by side, the one that you just pulse kicks up some dust, and then it gets entrained in it affects the cleaning of the one next to it. So you need to have an intelligent pulsing sequence as far as the rows of bags. That can show, that's kind of the hopper, where those are dust collectors, and the pulse valves are up above. Acoustic cleaning of filters can replace compressed air pulses, saving compressed air and extending bag life. So it's possible to use acoustic horns where you just blast it with something that generates a bunch of sound if you can stand the noise. And again, pulsing on differential pressure will also save compressed air. I don't know that I've seen, I know in the power industry, they will sometimes use acoustic horns to clean soot off of boiler tubes in a big boiler. But that's those power plants are out in the middle of nowhere, and so a little bit of noise out there, it disturbs the wildlife maybe, but it's not generally tolerated. But again, there's other ways to do these things. Okay, depressurized lines, that shows the solenoid valve that can be installed in airlines to particular processes and equipment to turn off compressed air when it's not needed. This eliminates leaks while there is no pressure because the valve's shut. So we've kind of talked through that before. Here is the timed drain trap. I think that's the same picture I had before, because that's probably the best picture I've ever taken of a time drain trap. But you see, this thing's going to fire every 15 minutes, and it's going to stay open for 10 seconds. So that's just a leak on purpose. We can use zero loss traps, and we don't want to use manual where somebody has to come open them, shut them, because they tend to crack them open and just let them bleed a little bit all the time, so they don't have to go back to them. Okay, let's see. So a lot of times there'll be a conveyor line, and we may be blowing moisture or material off product that's moving along this line. Sometimes there'll be a bar across the top that'll shoot down. Sometimes it has holes in it. Sometimes it has a slot in it, whatever. And, that's acceptable if that's what you feel like you have to do. But sometimes the line stops. And when the line stops, then you don't need to just blow compressed air at one point all the time. And so this is a system that a lot of times there's different ways to do this, but they'll have a sensor that can tell if the line is moving and there's actually parts coming by that need to be blown off. You can put a laser eye across this, and if that photo detector on the other side, if that's not broken like every minute, then it shuts off the compressed air, because it knows that there's no parts moving on the line. So, the use of those things can save a lot of compressed air, because sometimes these guys blow a lot of air in order. It could be moisture, or it could be dust, or it could be just cleaning off a product before it goes to packaging. A lot of that sort of thing gets done. These are induction nozzles or induction devices. And so if you feel like you have to blow compressed air on an object, or maybe you feel like you have to eject parts from a stamping machine with compressed air, you can, and you've got, say, a little tube. It could be a 1/4 inch, 3/8, half-inch tube that's blowing compressed air. Well, that can blow a lot of compressed air. Well, what you can do is you can put these induction nozzles on you can thread them or attach them to the end of that tube or pipe. And what they do, they have little holes in them right here that the compressed air comes out at really, really high velocities. And it's high enough that it induces ambient air that's around the nozzle up through these little flow channels. And so the overall impact away from at the discharge end of these nozzles and jets is pretty much the same as if it wasn't on there, but you use only half or less of the compressed air. And these things are not terribly expensive. Most of the time they're someplace around probably 30, 35 to 50, 60 bucks. And they will last a long time. Now, the issue is these little passages. If you have dirt and debris in your compressed air, these things can get stopped up, and then they won't work very well if that happens. But you can buy individual nozzles, or to put on one pipe, or you can have on a larger pipe, you can have a cluster of these things, but it has the same effect. So you get good impulse power from the compressed air out here at the end of the nozzle, and you don't have to use as much compressed air. And here, this shows one that has a whole bunch of these things, and they're pointing all kinds of different directions. This shows, this is they call it a super air knife. I forget, it's probably either Selvent or X-Air. Different companies make these types of devices. And so the compressed air flows in the inlet, and then it shoots out this very narrow slot. And it comes out with such velocity that it again induces ambient air with it. And so you get much more impact out here on the discharge side than just the compressed air. And so this will, what's it say here? It says it's free So air is entrained into the primary airstream at the ratio of 40-1. So for every 1 CFM you put through this thing of compressed air, you get 40 up to 40-1 CFM of ambient air induced into that discharge. So that's a pretty good device. Bunch of them out there. This shows, again, just it's the same device. It just kind of shows it blowing out. It could be drying produce. It could be blowing off dust. I mean, it could be doing all kinds of stuff. Oh, it also, these things also will, these induction nozzles reduce noise significantly. If you're just blowing air out of a tube, an open tube, I don't know, I guess I show that, but, and you put one of these nozzles on it, you will reduce the sound intensity significantly. And that's one reason that OSHA likes these things, because it does reduce noise levels in a production facility. Here's a couple of examples of some studies that were done a long time ago, just to show you some of the stuff that gets found. We have a spring and stamping plant. So the system has 2 compressors, 100 and 125 horsepower. Problem the plant was having is the compressors couldn't make enough air. So they were anticipating probably buying another compressor, which is probably a $35,000 to $50,000 proposition, depending on which one you buy, maybe more if it's a variable speed machine. So a study was done, and then some measures were taken, fixed leaks, replaced timer drains, the time drain traps, and added storage. Replaced Venturis with vacuum pumps, so they were doing vacuum generation. Add intermittent air controls and nozzles, and add solenoid valves to shut off air to idle machines. So those 4 actions were taken. Savings, they were able to turn off the 125 horsepower compressor and negating the need for a new compressor. So all of a sudden they had a backup. They didn't have to buy one. And so they saved $72,554 per year in energy with a $62,845 investment, and they didn't have to buy a new compressor. That's probably $120,000 or more savings to the plant. Avoided maintenance cost on the old and new proposed compressor, as well as capital cost on a new unit. So it had less than a year simple payback, which is pretty good investment. Because we're investing about 63,000, and we're going to save over 72,000. Pretty good. Here's another one, aircraft parts manufacturer. This has 75 horsepower and 200 horse compressors. Problem, system runs inefficiently, does not maintain pressure. So, a lot of similar, some of the stuff similar. Fix leaks, replace timer drains, and add storage. Install a smart sequencer master control panel. So put in a master controller to figure out what's the best mix of compressors, and which one should be the trim machine and which one should be base loaded. Replace blow-offs and air knives and nozzles. So they were just blowing a bunch of compressed air that they were able to avoid with some investment in different types of equipment. Reduce artificial demand, which means they reduce system pressure. Because remember, artificial demand is air that gets used simply because you have jacked up your pressure higher than it needs to be. And they installed a new cycling thermal mass refrigerated air dryer. And that was most likely in replacing a desiccant dryer, which, was probably venting either 7 or 15% of the compressed air rating of the dryer in order to regen the tower. So all that stuff together, they were able to turn off one of the 100 horsepower compressors and the 75 cycles intermittently, saved $87,000 per year with a $108,000 investment, 1.2-year simple payback. So that's pretty good. Pretty good examples, stuff that you can find. So here's a summary. It's a good idea if you're going to do a study, create a baseline. If you want to cut costs, baseline your system before and after each efficiency measure to try to evaluate how well it worked. Measure power, energy flow, pressure, and leak load. Estimate energy consumption and correlate to production levels. Maintain compressor and system pressure at the lowest possible levels, typically 2 psi is 1%, and that's for rotary screw and reciprocating. It can even be 1 psi is 1% if you're doing a bunch of blowing, but typically 2 psi is 1. On those now, centrifugal maybe not. It's complicated, more complicated on a centrifugal compressor, because when you drop pressure, you get more air. You may not reduce the power that much, and then the question is, do you actually efficiently utilize the air on the centrifugal? Avoid part load operation, which is usually inefficient, and certainly you want to have your most efficient trim compressor, your compressor that reduces load most efficiently as your trim machine. Measuring temperature can help you maintain compressors. If temperatures start going up, then it could indicate maintenance need. Could be a heat exchanger, could be problem with the compression element, probably some sort of heat exchange situation. And record all measurements when the system is new, and it's a great reference tool. Yeah, so you can say, well, we're running 105 degrees coming out of the package. What did we run when this thing was new? And the weather was, the same. So you can go back and compare. Measure and plot compressed air pressure and flow over time to understand your usage and system dynamics, weekends too. So, taking those measurements, amps, pressure, flows, and plotting them up will really give you a lot of information on how a system is operating. Where to start? Simple steps you can take. Walk through and look for low-hanging fruit, obvious measures you can do. Reduce compressor discharge system pressures. Look for and reduce compressor part load energy waste. Maximize the efficiency of air treatment, your dryers and your filters. Repair leaks, fix hoses, replace inefficient condensate drains, replace and eliminate inappropriate uses, turn off unneeded air compressors and treatment equipment. Performance improvements, well, this is kind of a laundry list. Reduce pressure, external intake for reciprocating and dry screw compressors, i.e. maybe get cooler air into them, can help. Reduce pressure at point of use, fix leaks, optimize pipe size and receiver storage, recover heat. Maintenance must be excellent. Audit uses continuously. What are we using air for? Do we really need to do that? No unnecessary compressors operating. Calibrate all measurement recording instruments. Explain cost. Eliminate excuses. That's a good one. Eliminate unnecessary pressure losses from the system. Optimize moisture removal from the system. Some other recommendations. Sometimes non-OEM parts don't work as well, hurt your efficiency. Dirty intake filters reduce efficiency, keep them clean. Dirty oil filters, you need to change oil and replace it as recommended. Test and change your lubricants per instructions, especially with extended life synthetics. Keep coolers clean. Maintain a clean, cool compressor operating environment. Try not to let that compressed air room that houses the air compressors get inordinately hot in the summer. Compressor sizing and selection. Understand your system demands and flow characteristics before selecting an air compressor. It does take a lot of study to figure out exactly what compressor would be best when purchasing one. Total kW output and/or specific power over the full operating range must be analyzed for a proper comparison with other types of capacity control. I mean, the VFD is great, but if you're going to run at 100% load, it hurts you. And it also adds a lot of expense to the compressor. So if you don't have any VFDs, then it might be a good option. If you already have some VFDs for trim, maybe if, you're replacing a compressor that would run at full load, so there's not a need for it. No compressor is perfect for every system. Reliability and durability should be considered. Many demands are intermittent, but the worst case scenario must also be considered. Need a backup compressor to cover the largest compressor. So the rule of thumb is you ought to be able to have enough extra compressors around that you can lose your largest air compressor due to a maintenance issue and have enough to turn on so that you can continue to operate successfully. Consider multiple compressors networked together for multi-shift operations. And of course, you need an intelligent control system with that. Centrifugal and rotary are better suited for continuous baseload type service. Rotary screw compressor with VFD capacity control is an excellent part load compressor. Small single acting reciprocating compressors are excellent for small plants as well as small high pressure applications in a large plant. So I think we had mentioned this previously, but you may have a big plant that has one or two small air uses that require a much higher pressure. And instead of jacking the pressure on the entire system, you simply put in a small dedicated compressor to take your lower compressed air pressure and boost it for those applications. Consider increased storage air receivers. More storage is always good. Understand your system demands and size the compressor to match. Consider reasonable growth, but don't oversize for something that may not happen. Just some typical calculations. Annual electricity cost. We've been through this, so you can get an estimate for the year if you have an average current draw times the voltage. This would be RMS times, that's the square root of 3, power factor, times the number of hours, times the rate. That would be dollars per kilowatt hour, and then divide by 1,000 to convert from watts to kW. And so here's a little example of 250 amps, 460 volts, square root of 3, 0.85 power factor, 6,000 hours, and 10-cent power. Almost 104,000 a year. Gets into real money pretty quick. Brake horsepower is the measured horsepower delivered. Yeah, that's out of the motor into the shaft. We know that. 2 are required at the compressor shaft. Most compressors use part of the service factor designed into the motor. So whatever the brake horsepower is times 0.746 converts to kW, and then so that's kW times hours times rate divided by motor efficiency, because remember the brake horsepower is in the shaft, and so to get the input power to the motor you have to divide by motor efficiency. Annual energy cost calculation exercise. Assume we have 110 brake horsepower, because we're, the service factor, 15% service factor would say that we could use 115 horsepower. So we're taking 2/3 of that service factor. So that puts us at 110 at full load. Motor efficiency is 93%, operating hours 8760, and we're 10-cent power. So there you go, plugging the numbers in, over $77,000 a year. Note, this is a full load calculation and is not include correction for part load and the fan brake horsepower for air-cooled compressors. So if that's just the compressor motor, then you've probably got a 5 to 10 horsepower fan if it's air-cooled. That for the total package, energy use would have to be added in as well. Summary: compressed air is important. Plants can't really operate without it. Compressed air systems start with the supply side. Compressed air systems go beyond the compressor room. Baselining is essential to manage a compressed air system. Systems can be controlled. The efficiency of compressed air system can be maintained by developing and implementing a plan. You can ensure your compressed air system is efficient and cost effective. Questions? All right, I'm going to cut this off right now. I may dig up some other slides and get those posted later, or I've got some other things that I'm going to show you for Thursday's final lecture. So I'm going to post this as part of Tuesdays, the second part of Tuesdays, and then there'll be more coming shortly. Hope you guys have a great day, and I'll be back in touch.